Got to record the meeting, but anyway, just do that. So question, which type of sodium do you use? You use the sodium ion. Sodium ion is much, so when people say, okay, I'm on a low sodium diet, they certainly aren't talking about sodium metal, because nobody would eat sodium metal. What would happen is the sodium would contact water and pretty much it'll catch on fire. And so you don't want to be touching sodium metal, even with your fingers, you know. So nobody touches it. And so sodium ion is what we're talking about. And so, you know, there's always that distinction. So we have to be careful when we name things, you know, otherwise we could be taking the wrong stuff. You know, like when iodine, for example, you know, iodine, like, you know, you need, what happened recently, Fukushima, you know, the Fukushima nuclear plant, you know, they had the meltdown there and that released a lot of radioactive iodine. So one of the prophylactic measures for minimizing radioactive iodine absorption is to saturate your thyroids with non-radioactive iodine. And so, you know, a lot of people don't get enough iodine in their diet. When Chernobyl happened, you know, they did a study. Some countries there supplied iodine to their kids and citizens, and other countries didn't. And the countries that supplied iodine, the non-radioactive iodine, to their children saw a much lower thyroid cancer rate than the countries that didn't supply iodine. And so, well, what kind of iodine are you talking about? Are you talking about elemental iodine? Elemental iodine is an oxidizer, and it's used to kill bacteria and whatnot. That's iodine, elemental iodine. Or are you talking about iodide? Well, we're talking about iodide, you know. Iodide, we need iodide in our thyroid. Iodine is it's an oxidizer, so it can cause some tissue damage as well. But, you know, in small amounts, maybe iodine's okay. Iodine's going to oxidize something, it's going to gain electrons and gets converted into iodide, which is more stable form. And so, so some people were talking, well, there's a shortage, you know, around the time Fukushima happened, there was kind of a shortage of iodide going around. So some people were substituting iodine for it instead. And so I guess in small quantities, that would be okay, but in large quantities, iodine would be more problematic. And so you have to be careful because it's not always clear when people are talking about things, you know, because of nomenclature. That's why in chemistry, chemists are very concise in their definitions of nomenclature. That way we can avoid confusion about these things, you know. Yes, Kazar, we only use the prefixes, di, you know. Bi, we don't use. Bi is for acid anions. Di, tri, tetra. You know, omit the bi. When we see bi like that, Bi, we think of bicarbonate, a hydrogen carbonate, you know, acid anion type thing, deal. That's what I think of usually. All right, let's take a look at some more nomenclature. Although I have to get into chapter 7 today, and so I need to do that as well. But what I'll probably end up doing is I'm going to go through it quite quickly through some additional practice nomenclature. And so let me zip through some of this and then we'll start chapter 7. And so the nomenclature problems, there are actually quite a lot, almost 100 nomenclature, actually more than 100 if you break it up into parts. So I'll get through as many as I can, and then we'll start chapter 7. But it's time for our break right now. So let's take a break. I forgot to record, so all that earlier stuff, but some of that stuff we'll be talking about again. I forgot to record the earlier stuff about oxidizers, reducers, but again, we'll see that one more time. Shoot. Okay, so I'm going to pause the recording. Let's take a 15-minute break. So it's like about 12:40 now. So we'll meet back at 12:55. All right, so 12:55. No, I didn't record the first part of that lecture today, but all right, let's continue on. I posted a link here for nomenclature, so you can go ahead and upload that. We're going to continue on looking at some nomenclature problems, and now I'm going to go kind of quickly through these to see what we're doing here. Actually, I'm going to skip the ones with the answers. I'll just look at the ones without the answers here. Write the chemical formula of each of the following. The compound, you should look at the ones with the answers if you want additional practice. Go through these here. Write the chemical formula of each of the following. A compound made up of a crystal with 2 particles coming from chromium for every 3 particles coming from oxygen. And so let's go ahead and write that, and we're going to name that too. And so I'm going to do that here. So we got 2 chromiums and 3 oxygens. Now, typically what happens is, you know, the cations are typically on the left side of the periodic table. And so these are usually written first. And then on the right side are the anions, you know, because remember on the left side we have, what are these called? These are called reducers, and reducers tend to lose electrons. And over on the right side we have the oxidizers, which tend to gain electrons. So the oxidizers gaining electrons are going to form the anions, the reducers losing electrons will form the cation. And then if the oxygen gets its normal charge, which is 2-, oxygen might not have its normal charge, you know. The other charges for oxygen would be like -1 in peroxide and something called -1/2. That's the average. You know, you can't have half an electron, so it's like a -1 on one oxygen and 0 on the other oxygen in superoxide. Then we have 2 chromiums. And so here, what must be the charge on chromium for this to add up to 0? There's no charge on this compound. And so the charge on chromium must be, the chat window here. It's got to be, you know, -6 and +6, and so that means each one must be +3, you know, or 3+. You can write it +3 or 3+. You know, I write it different ways depending on the context here. Like oxygen, you see I wrote it as 2-. You know. The compound made up of a crystal with 1 particle coming from barium for every 2 particles from okay, BsCO2. Now chromium's variable charge. The common charges on chromium are +2 and +3 because it's in this range. It's +2 +3, or +1 +2, +2 +4. And so it's +2 +3. And so this is called chromium, Roman numeral 3, oxide. Chromium, Roman numeral 3 is all one word, and we need the parentheses there. Or chromic oxide. Chromic is the higher charge. Chromos would be the 2+. Barium's fixed charge, so this is just barium chloride. We wouldn't call this barium dichloride. The reason we don't call it barium dichloride is we only use di for molecular. Well, barium's a metal. Molecular compounds are non-metals. So if this were non-metal and non-metal, I'd use dichloride. But since this is a metal, we know barium is 2+, and therefore we don't need di because we have to have 2 chlorides to balance out the +2 on barium. So this is just called barium chloride. A compound made up of molecules with 12 carbon atoms, so C12, 22 hydrogens, H22, and 11 oxygens. Now this is not binary, so we wouldn't call this dodeca carbon or whatever. And then say, I forgot 20. There are all kinds of names for this. We could name these. This is not binary, so we don't use the little prefixes. And I didn't teach you the prefixes beyond 10. And so we don't do that. This is using a different set of rules. This is actually a sugar, and its common name is sucrose. This is table sugar, C12, H22O11, table sugar. The compound made up of molecules of 3 hydrogen atoms, 1 phosphorus, and 4 oxygens, H3PO4. H3PO4, I recognize PO4, that's PO4 3-. PO4 3- is phosphate. So this should be phosphoric acid, or better said, phosphoric acid. Phosphoric acid. It's going to have 3 hydrogen ions there to do that. And so let's continue on here. See, it's 1 now. Continue on here, next page. Let's clear these drawings. Okay, this has answers, this has answers. You should go with, you know, like I said, you should go through and do the ones with the answers on your own, so I'm not going to do them. Write the formulas of all elements that exist as diatomic molecules under normal conditions. There's 7 of them, and you should know all 7. If we look at the periodic table, it's pretty easy to see, you know, it's H, and then it starts off with N, and then O, and then what comes after O? Cl, or F, sorry, F, Cl, Br, I. So it forms this little, you know, this shape in the periodic table. So we could see the pattern in the periodic table, but there's 7 of them: H2, N2, O2, F2, Cl2, Br2, I2. It's 7. These are the 7 diatomic molecules. And so, you know, if somebody's talking about oxygen, it's most likely O2, but it could possibly be O, you know, because how much oxygen is in a water molecule? They're talking about O. They're not talking about O2. There's no oxygen gas in water molecules. It's just an oxygen atom. And so, you know, it's not clear. When somebody says oxygen, it's not clear if they're talking about the diatomic or the single atom. Now, we need the context of the question to clarify that for us. Okay, given the names, write the formula. So germanium is just Ge, and it's a solid. It's a semi-metal. Fluorine is a non-metal. It's a F2, it's a gas. Argon is a non-metal. It's a noble gas. So those like to be alone. They're stable. Gallium is a semi-metal. It's Ga, and it's a solid or metal. You know, gallium's almost a metal. Okay, and now let's go on to naming these things here. As we go down, I need to, well, actually, I'm not going to scroll down now. O2 is oxygen, or more specifically, molecular oxygen. That would clarify that, you know, if we're talking about O2 or O, you know, called molecular oxygen versus atomic oxygen. Ca is calcium, Ba is barium, Ag, what's that? Ag is silver. Okay. Yeah. If you don't know those, you know, you start memorizing them. And let's take a look at this next one here. Okay, let's write the formulas. Carbon's on the right. So this looks like carbon. That definitely does not look like diamond. I don't know what that looks like. That looks like maybe amorphous carbon, maybe graphite. It's kind of shiny. Graphite's a little darker in color, but color is always deceptive. And so go ahead and write the formulas. Oh, actually, these have the answers, so I'm not going to write it. Chlorine, let's do these. So chlorine, we have a choice. Chlorine, they're either talking about molecular chlorine, Cl2, which is the most stable, or atomic chlorine, you know, or atoms of chlorine. Like in the chlorinating agent, you know, there are atoms of chlorine in bleach, which is a chlorinating agent. Magnesium is just solid. There's a chlorine gas. You know, chlorine's, atomic chlorine is quite unstable by itself, but, you know, if you have chlorine in a compound like sodium chloride, you know, it's different than having chlorine gas. You know, in sodium chloride, we have chlorine atoms. They're ions in this case, or we could have other things with chlorine in there that aren't ions, that are molecules. Like what would an example of that be? Something like PCl3, you know, phosphorus trichloride, you know. Nitrogen N2 is most likely what they're talking about, but we could have atoms of nitrogen. Vanadium, it's just vanadium solid, atoms of vanadium. This is going to be a lattice structure. This is going to be a lattice structure. These are molecular structures or atoms. Let's move on. Okay, we're either going to write the name or the formula. This is a binary molecular compound. It's molecular, it's non-metals. Carbon's a non-metal, chlorine's a non-metal. There are two elements, it's binary molecular. So here we can just use the simple binary molecular nomenclature rules. This is a liquid, actually, carbon tetrachloride. Carbon tetrachloride. It's a liquid. This is carbon tetrabromide, so same thing. This we saw earlier. This is nitric oxide or nitrogen monoxide. Dinitrogen monoxide is N2O or nitrous oxide. Sulfur dioxide is SO2. This was nitric oxide, or nitric oxide is its common name, or nitrogen monoxide. Nitrogen monoxide. Monoxide, not monooxide. Sulfur dioxide is SO2. It's a binary molecular. All these are binary moleculars. Sulfur hexafluoride. Sulfur, 1. Fluorine, hexa, 6. So SF6 is a gas. This is a stable gas. You wouldn't expect this to be a stable gas because sulfur, if fluorine's happy at -1, we have 6 of them, then that must mean sulfur has got to be +6. +6. That's very high. And so you'd think this would be like perchlorate, explosive, but it turns out that this is stable, fairly stable. It's not explosive. I would tend to think it's explosive when reacting, as an oxidizer. Oxidizers want electrons. And so as an oxidizer, it looks like sulfur is really short of electrons, so it probably wants to take them from something else. It turns out it's not as reactive as you might think. It's stabilized by all these fluorines on here. So it turns out to be fairly stable, unexpectedly, when we compare that to other things. But sulfur is okay losing, electrons compared to something like nitrogen or chlorine, which is going to be much more reactive. Those are much less okay with losing electrons. Those do not really want to lose electrons. Selenium is even more okay. As they get bigger and bigger, they tend to be less and less reactive, the atoms. Let's continue on here. Let's clear these drawings here. Write an equation that shows the formation of rubidium ion from neutral rubidium atom. And so there are different ways we can write this equation. First, we got to find out where rubidium is. Rubidium is a simple Rb, and it's an alkali metal. And so it's like this. It's lithium, sodium, potassium, rubidium, cesium. So it's sandwiched between potassium and chlorine. It's pretty big, and so it's easy to lose this electron. Rubidium loses this electron easier than potassium. Potassium loses this electron easier than sodium. Lithium has the hardest time losing electron, reactivity-wise. So the most reactive is cesium here, because cesium is the biggest, and it's easy to lose that electron. Cesium's big. It would be like cesium. So rubidium loses that electron, it forms a rubidium ion plus an electron. And so we can see how many electrons does rubidium have, And so we take a look at rubidium. This is such a slow process. Let's take a look at the periodic table really quick. Misspelled table, but it's all right. Yeah, give me a decent periodic table here, please. Come on, without having to click through so many. Rubidium has 37 electrons and 37 protons. If we lose one, we're at 36 electrons, which is krypton, and 37 protons. The number of neutrons varies depending on what isotope we're talking about. And so, 57 electrons and 57 protons. So we could add that in here. Get the right pen up here. So 57 electrons and 57 protons. And the number of neutrons varies depending on the isotope. And then it's going to be close to 57 neutrons. It depends on what the mass is. I mean, if we go and look at the mass, we can get a guess. You know, the average, we look at the periodic table, the average, oh shoot, this one doesn't have the average mass. This, nor does this one. Give me a periodic table with the average mass of rubidium. This one does. Oh, please. Rubidium has an average mass of 85 and a half. 85 and a half is the average mass. So 85, a proton's about 57 U. And so 85 would be another, what? Is that right? It seems off. Yeah, that's right, 37. What am I doing, 57? It's off because it's not enough. 37, I made a mistake because the ratio came out way off. It should be, you know, typically it's around the same number, you know. Sorry, I made a mistake. 37. 37 electrons and 37 protons. And so the rubidium ion, what happens when we form the ion is something very interesting. The atom's bigger and then it shrinks to about half the size. So the ion is a lot smaller. Cations are a lot smaller. When we lose that electron, anions contract. Anions tend to be bigger. So when we form an anion, the anions grow about double in size. When we form a cation, the atom shrinks by about half the size. And that's because of this imbalance. Now we have 36 electrons and 37 protons here. And so it shrinks that. And so the rubidium ion is about half the size of the rubidium atom here. That's for positive. For negative, it doubles in size. So iodide, I minus is about double the size of an iodine atom here. Okay, so this is an example of the equation that shows it. About how many neutrons, if we were to take a guess about how many neutrons, the average mass is 85. So it's about 37. If we have 37 neutrons, no, that would be 74. It would be closer to 50, 40, it'd be closer to 48, you know, 48 neutrons, closer to that. That would give us about 85. Would that be right? Yeah, about 85. So around there. What are the names of O2 minus? O2 minus is oxide and I minus is iodide. Oxide and iodide be the names. Okay, let's move on. Okay, I got to pick up the pace here, otherwise I'm going too slow. So this is just a quick blast through this. So I'm not going to spend too much time on any particular problem. What are the formulas of tin 4 ion? Okay. Tin 4 is just SN4+. Okay. Again, you could write it as a 4+ or +4, you know, but oftentimes it's written like this. Manganese 3, it would be Mn3+. You know, it depends on the ion, you know. The way I write it. Okay. Here they wrote it in that convention. This is, of course, Pb2+ is lead, but it's variable charge. We have lead 2 and lead 4. It's a 2,4. So this is where lead Roman numeral 2 or plumbus. Plumbus is the old name for that. Plumbic would be the 4. And CO, cobalt's a 2,3. So this would be cobalt Roman numeral 2 or cobaltus. Cobaltus would be the lower charge. The higher charge would be +3. The cobaltus ion would be the old name for that. Let's clear this. What are the formulas of lithium nitride? Okay. Lithium is off the periodic table. Both of these are right off the periodic table. Lithium is fixed charge at +1. Nitride is fixed charge at well, -3. I mean, in a way, it's sorry, nitrogen wants to gain 3. It's ide, so it's monatomic. You have to know the polyatomic ides like hydroxide, cyanide. But if it's an elemental ide, nitrogen, as the anion, it's 3 minus. So lithium nitride is we need 3 lithiums to balance out the -3 here. So Li3N lithium nitride. It's a solid. As most ionic compounds are solids. Chromium 2 chloride. Okay, chromium, what's the formula for that? It's Cr. Okay, and it's 2+. And chloride's -1. So we have 2 chlorides and 1 chromium 2. So this is going to be CrCl2. Aluminum phosphide. Okay, aluminum is 3+. And then this is an ide, so it's monatomic, unless it's one of the polyatomics we memorize. It's phosphorus. Phosphorus is 3 electrons short. And so that. This is just, well, that works out. We need 1 aluminum and 1 phosphorus, AlP. Tin 4 bromide. Okay, tin 4 is SN4+, and bromide is Br-. And so we're going to need more bromides here. In fact, we're going to need 4 bromides here to balance out that +4 charge. So this is going to give us SnBr4 for that. And so that's that. What are the names of MnF3? Okay, manganese is Mn, but manganese is variable charge. So we need the Roman numeral. We've got to figure out what the charge is. We can figure out what the charge is by looking at fluorine. Fluorine's charge is, we know that fluorine's charge is -1. So 1 electron short. And therefore manganese must be, well, it's got to be +3. And so that's the higher charge. Manganese is 2,3. So this is manganese 3. And so MnF3, oops. In other words, this is going to be called manganese 3, Roman numeral, fluoride, Fluoride, or manganic. You know, it's a 2,3, so manganic is going to be the higher charge, or manganic fluoride. Nickel is a 2,3 also. Your book calls it a 2 only. Your book calls nickel fixed charge, but it's variable. And the most common charges for nickel are 2 and 3. 3 is much more rare. Nickel 2 is much more common. So this is why your book calls it fixed charge at +2, but there are nickel 3 compounds you can buy. And so I don't call it a fixed charge. And so this is going to be nickel 2 or nickelus. This would be nickelic, but we aren't going to use it. I'm just going to call it nickel. Now, there are different spellings for nickel, you know, depending on if you're English or American English or British English or something. So nickel, we'll call it this one. Nickel, Roman numeral 2. And then this is got to be S. I know it's 2-. S is 2-, therefore nickel, it's got to be nickel 2+, because S is 2 electrons. S is in the same family as oxygen, so S likes 2 electrons. And so this is nickel 2 sulfide here. All right, this is lead, and lead is lead 2 or lead 4. And so we have a choice here, but I know it's got to be lead 4 because we have 2 oxides. We got 2 oxides, those are -4 altogether, and so that means lead has to be 4+. And so this is PbO2, which is lead 4 oxide. Lead 4 oxide. Lead 4 is the higher charge, so we couldn't call it plumbic. This would be plumbic oxide. It would be an alternate name for that. Cobalt is a 2,3, and so we got to figure out what the charge is on that cobalt. But we could do that based on sulfur's charge. So we have 2 cobalts, and we have 3 sulfurs. The species on the right always get assigned first, the charge that they like. The species on the right usually gets assigned first. And so sulfur is going to get assigned first, 2-, because the oxidizers usually take precedence. So that means this is -6. That means cobalt has to be a total of +6. That means each one of these has to be a 3+. So this is the higher charge cobalt. The lower charge cobalt is cobalt 2. So this is cobalt 3. sulfide, cobalt-3 sulfide. Or cobaltic sulfide. Cobaltic would be the 3, cobaltous would be the 2. And so, cobaltic sulfide. You wouldn't use cobaltic Roman numeral 3. You know, that would be redundant. Do something. Somebody keeps. Just give me a moment here. Okay, I'm back here. Let's take a look. Let's see, 122. All right, how do you recognize formula of acid, H? What element is present in all acids discussed in this chapter? Hydrogen. Hydrogen is present. Which of the 5 memorized ic acids? Okay, I don't solve it like they did. I don't memorize the ic acids. So I do it a totally different way. If their way makes sense to you, do it their way. You know, fill in the blanks. Okay, let's fill in the blanks here. Oh, actually, this has the answers there, so I'm not going to do it. Okay, let's fill in the blanks. What's the anion here? And so the anion is chloride. It's an ide. And so we have to use the hydro and the ic acid. And so this would be hydrochloric acid. This is an ic acid. There's no hydro here. And so it's nitric gets changed to nitrate. And so that must mean we have nitrate. You know, nitric gets changed to nitrate. And nitrate is NO3 minus. And then we add the hydrogen to that. How many hydrogens do we need? H pluses? We need just 1. So it's HNO3. To add the H plus, we got to add enough H pluses to cancel out the negative charge. And so in this case, we only need 1. This one is, let me blow this up a little bit. Actually, I'm gonna be able to do all of them. Let me see if I can open this window. All right, we'll just do it off this window. I don't want to resize this thing, but it doesn't let me resize this bigger, unfortunately. All right, this anion is PO4, and it's got to be 3 minus because we have 3 H pluses there. You know, H plus, H plus, and H plus. This is PO4 3 minus, which is phosphate. Phosphate, it's an 8, so we just change it to ic acid, so phosphoric acid. This is hydro-ic. Hydro-ic means it's got to be an ide, and so it's sulfide. This has got to be sulfide, S2 minus. So hydrosulfuric acid is we add enough H pluses. Well, we're going to need 2 H pluses, and so this is going to be H2S. H2SAQ. This is a case where we have that weird rule I talked about earlier. H2S gas is pure. This is called hydrogen sulfide gas, or Rodnay gas. Hydrogen sulfide. It's toxic. Hydrogen sulfide is very dangerous because what it does is it saturates your olfactory sensors and you stop smelling it. It smells awful, but pretty soon you become desensitized to it. And it's lethal at the part per billion level. So you can die without knowing. You know, if you start smelling this, you got to get fresh air to clear your olfactory sensors. If it's H2SAQ, we call it hydrosulfuric acid. This is hydrosulfuric acid. And so this is the same thing that we saw for HCl. You know. Okay, HNO2 is NO2 minus. NO2 minus is nitrite, and so it's an ITE, ITE, so this is going to be nitrous acid. Hydroselenic acid, so this has got to be selenide. Selenide's in the same family as sulfur, so it's this S2 minus, so this has got to be H2SE, aqueous. HClO4, well, ClO4 minus is perchlorate, you know, the very dangerous stuff. You know, it's dangerous if it's stable as long as you don't give it something to react with. HClO4 is stable because H plus has already lost an electron. So Cl4 minus can't take an electron from H plus. It has no electrons. And therefore this is stable. You know, it's not going to explode, HClO4. It's only going to explode if you put something in there that has electrons it can take. And so this acid, we don't have to worry about it exploding, but this is perchlorate. And it's an 8, so we just change the ending to perchloric. It's perchloric acid. And so perchlorate gets changed to perchloric acid. Hydro, we got the hydroic. Again, hydroic, this has got to be iodide. Iodide is I minus, so hydroiodic acid is HI. This is chlorite. Chlorite is ClO2 minus. So chlorite gets changed to ous acid, so this is just chlorous acid. And then we go to selenic acid. Ic acid means this has got to be selenate. So what is selenate? Selenate is, we know what sulfate is. Sulfate is SO4 2 minus, so selenium is right under there, so it's SeO4 2 minus. So selenic acid is selenate, SeO4 2 minus, and we add enough hydrogens, and so we'll need 2 hydrogen ions to balance that out. So it's H2SeO4, this would be selenic acid. BrO2 minus. BrO2 minus is bromite. Bromate is, you know, 3 oxygens. Bromite is 2 oxygens here. And so bromite, this has got to be bromous acid. Bromous acid. We just change the I to so. What are the formulas of carbonate? Oh, let's skip that one. You can do that one yourself. You have the answer. What is the formula of arsenate ion? Okay. Arsenate's just like phosphate. We see that in the periodic table. It's ASO4 3 minus. This has got to be, well, tellurate, sulfur, well, oxygen, sulfur, selenium, tellurium. They're all in the same family. Sulfate is SO4 2 minus. Sulfite is SO3 2 minus. And so TeO3 2 minus has got to be tellurite. This is tellurite. Tellurite. IO3, well, that's in the 3 oxygens. This is just iodate. You know, looking at the periodic table, we should be able to see these right away. What are the formulas of zinc nitrate? Zinc is fixed charged, Zn2 plus. Nitrate is from the periodic tables, NO3 2 minus. So we'll need 2 nitrates for every zinc, so Zn. Now we have to use parentheses here. If we don't use parentheses, it looks like I have 32 oxygens. I don't have 32 oxygens, I have 2 nitrates. So I need parentheses there. When you use parentheses, you only use parentheses if it's going to be confusing otherwise. You know, don't use parentheses unnecessarily, because if you use parentheses unnecessarily, it's wasting paper. And so here it's absolutely necessary. Calcium selenate, calcium's fixed charge at 2 plus. Selenate is like sulfate, and so selenate's got to be SeO4 2 minus. So selenate's SeO4 2 minus. And so calcium selenate is 1-to-1, you know, they balance each other out. CaSeO4. Okay, this one, you should recognize this one, and you should recognize this one. Bromate was 3 oxygens, so this is 2 oxygens, and so that's bromite. And so this is bromite, and it's BrO2 minus, and this is NH4 plus. NH4 plus is ammonium. Ammonium is what we call electron rich, and so if you had ammonium and perchlorate, then that's going to be explosive. And so ammonium bromite is the name of this. And so ammonium spelled with 2 M's, ammonium bromite. Would be that. Gosh, all right. I logged out. I'll log back in. Okay, let's see, we finished that. Let's go into this one. Write equations for the first and second steps in the step-by-step ionization of selenic acid. All right, I guess I didn't talk about this at all. What they're talking about ionization here is they're talking about dissociation of the H pluses. They teach acids and acid ions a little bit differently than I did. And so they teach it by memorizing the acids first. I teach it by doing the anions first. And so they're going in the opposite direction. And so let me show you what they mean here. And so let's take selenic acid, and that's selenate. Ic acid goes 8. And so selenate is SeO4, 2 minus, so H2SeO4 is selenic acid. If we take selenic acid and lose 1 H plus, then we're left with HSeO4 minus. This is what they're calling the first step of ionization. That is knocking off an H plus and creating the ions here. This is the hydrogen selenate ion or the biselenate. So this is selenic acid. This is the acid anion, hydrogen selenate. And in the second step, we knock off the next hydrogen. So we're going to keep track of all the hydrogens. So now we'll have a total of 2 hydrogens altogether. This one plus the second one. And we're going to be left with selenate, SeO4 2 minus. And so we have selenate, hydrogen selenate or biselenate, and selenic acid here. So this is the first step. This is the second step here. Okay. I'd go from the anions, and then I'll just add an H plus to get to hydrogen selenate, add another H plus to get to selenic acid. Doesn't matter which way you do it. Yeah. What's the difference between ite and ide? Okay, the major difference. Ite usually refers to having an oxygen-containing anion, so we call them oxyanion. An ide usually refers to monatomic. That is a single element anion. And so look at chloride versus chlorite. This is chlorite with a T. This is chloride with a D. It's an oxyanion. We were looking at some of them the other day in the periodic table. You should know, when you look at chlorine, what are all the anions or in cations? You might see that. Well, we see chloride, we see chlorate, we see chlorite, we see perchlorate, we see hypochlorite. And so you should know all the variations of the species that you see for these. Look at chlorine. You do that for every element. You could do this for every element once you go through your notes so many times, you've seen all these already. And once you do this for every element, then this becomes logged in your mind. you know, the differences and what they are. But that comes from repetition, just repetition, repetition, repetition. Pretty soon, you know, it's hard initially, like riding a bicycle. Learning how to ride a bicycle is hard initially. But after enough repetition, it becomes routine. It becomes easy, just like that. You know, it'll become routine and easy. And once you do it enough times. Dihydrogen phosphate's acid anion here, and dihydrogen phosphate's just going to be H2PO4. Now the phosphate's 3 minus, and then we have 2 positives, so it's negative. Hydrogen sulfate's another acid ion. We'll take a hydrogen and a sulfate, SO4. Sulfate's normally 2 minus, plus 1 gives us minus. Hydrogen tellurite. Tellurite, now tellurate is like sulfate, you know. It's in the same family, and we know the pattern in the periodic table. And so this TeO4 is tellurate. TO3 must be tellurite. It's got the same charge. And so hydrogen tellurite ion is going to be 2 minus on the tellurite plus 1 plus on the hydrogen. Gives us the negative charge. Yeah. This is a hydrogen carbonate or bicarbonate. This is hydrogen tellurate. This is hydrogen tellurite. This is hydrogen sulfite or bisulfite would be these. And so this is hydrogen carbonate. Actually, let me go through these quick. You can always go through the recording if you need to back up and see this. I need to go quicker. I don't want to waste too much time here. Hydrogen tellurate or bitellurate. Hydrogen sulfide or bisulfite. So, it is often possible to change a hydrate into an amorphous compound by heating it. Anhydrous, excuse me, hydrate and anhydrous. I haven't talked about these. I need to talk about these. I didn't talk about naming hydrates. A hydrate has waters that are trapped in the crystal. And so when I look at magnesium sulfate, for every magnesium sulfate formula unit, I have 7 waters trapped in the crystal. What happens? This is called a hydrate. And so this would be magnesium sulfate 7 hydrate, or magnesium sulfate hepta. Hepta means 7 hydrate. So one way we can drive off the waters, these are waters trapped in the crystal lattice. It doesn't look wet. You know, this is Epsom salt. When you look at there's 7 waters trapped for every magnesium sulfate formula unit here. It doesn't look wet, it looks dry, but it's not dry. We have to dry it in an oven to make the anhydrous form. The anhydrous form has no water trapped in there. And so we heat it up to drive off the water and dehydrate it. Write an equation that shows the dehydration of potassium fluoride dihydrate. And so potassium fluoride is Kf, and then dihydrate means we have 2 waters stuck in the lattice. This is a solid. And the waters are not, you know, the waters are like water vapor gets trapped in the lattice here, the maze of the lattice. And then we heat it. When we heat it, we can drive off the water steam. So we're left with potassium fluoride solid plus H2O gas. We can drive off as steam. Now we need 2 waters to drive off for every formula unit of Kf. Drive that off. Yeah, I forgot to talk about hydrates. How many water molecules are associated with the 1 formula unit of calcium chloride? Okay, when I look at 1 formula unit of calcium chloride, I have 2 water molecules. So for every single calcium and 2 chloride ions, I have 2 waters stuck in the lattice. Write the compound, the name of this compound. So the name of this is just calcium chloride, this here. And then when we have the water that's stuck in there, calcium, this is a solid, by the way, calcium chloride. Now we could use the prefix, 2 is di, and so we call it dihydrate. Calcium chloride dihydrate. The compound barium perchlorate. Barium perchlorate stable. Barium's already lost its electrons. You know, barium's 2+. Perchlorate is ClO4-. So barium's already lost its electrons. It's not going to lose any more. So this is stable. This is not explosive. And then we need 2 chlorates for every barium. So the formula is going to be BaClO4, 2. Forms a hydrate with 3 water molecules per formula unit. What is the name of the hydrate? What is its formula? So for every one of these units, you know, barium 2 perchlorates, we have 3 waters. So we write a little dot, 3 H2O. It's a solid. And so what we do is we call this barium chlorate trihydrate. Barium perchlorate trihydrate. Barium perchlorate trihydrate. Okay, like that. We could dehydrate this by heating it up, and they'll drive the waters right out of they're stuck in the lattice. You can drive them right out of the lattice. Barium nitrate, I guess what do they want? They want us to write the formulas. Write the formulas, all right. So you can do this quickly here. Barium is fixed charged, 2+. Nitrite is nitrate is NO3, nitrite is NO2, charged minus. And so we'll need 2 nitrites for every barium. NO2, 2. Sodium hydrogen carbonate. Sodium is plus, and then the hydrogen carbonate is an acid anion. Carbonate's normally 2-. We got an H on there, so it's going to be 1-. So sodium hydrogen carbonate is just NaHCO3. So sodium bicarbonate, which is baking soda. Aluminum is fixed charge, that's +3. Nitrate is NO3-. We got to be quick on the periodic table, and so we'll need 3 nitrates to make sure the charge is balanced. So this is going to be Al. We need parentheses here, NO3, 3. Calcium chromate. Calcium is 2+. Now chromate you have to have memorized. They're giving it to you, but that's not adequate. You have to have it memorized. There's a chromate CrO4 2-. So calcium chromate is CaCrO4. That's it. It's also solid. Let's see. Okay, next, aluminum bromide. Okay, bromate, we see from the periodic table, it's in the 3 oxygen, and it's charged minus. That you should be able to get quickly. Aluminum's 3+. So aluminum, we need 3 bromates. So it's going to be Al with 3 bromates here. But this is also solid in pure form. You know, you dissolve it in water and get it dissolved in water, which we call aqueous. Potassium dichromate. You should know dichromate. You shouldn't have to have that given to you. Potassium is fixed charge of +1. Dichromate is Cr2O7, 2-. So we need 2 potassiums. Here we do not need parentheses. There's no confusion. Without parentheses, we have 2 potassiums and 1 dichromate, Cr2O7. This is potassium dichromate, which is an orange solid. Barium dihydrogen phosphate. Barium's fixed charge at 2+. Dihydrogen phosphate is an acid anion, H2PO4. Phosphate's 3-, 2 hydrogens. This is going to be minus. So we need 2 dihydrogen phosphates for every barium. So it's going to be BaH2PO4, 2. Here we need parentheses. Rubidium selenate. Rubidium's Rb+, fixed charge. Selenate. Selenate's like sulfate, SeO4, 2- here. And so we'll need 2 rubidiums. Here we do not need parentheses, Rb2SeO4. So cobalt 2 hydroxide. Cobalt 2 is cobalt 2+ hydroxide. You need to memorize that. It's not monatomic. This is an ide that's polyatomic. Hydroxide, cyanide, like the superoxide. And so we'll need 2 hydroxides for every cobalt. Zinc chloride. Zinc is fixed charge at 2+. Chloride's fixed charge at -1. So ZnCl2 will do it. Lead 2 nitrate. Lead is 2+. Nitrate is NO3-. So we'll need 2 nitrates for every lead. So we got Pb. We need parentheses here. NO3, 2. Copper 1 nitrate. So copper as a 1,2. So copper 1 is just copper plus 1. Nitrate is NO3 minus. And so they nicely balance CuNO3. It's copper 1 nitrate. That's also solid in pure form.
Other brother.
Okay, let's continue on here. When I look at PBS, first I look at sulfur. What's the charge that sulfur wants? The charge that sulfur wants is 2 minus. So this has got to be lead 2 plus because I only have one of them. So PBS is lead 2, Roman numeral 2 sulfide. Lead 2 sulfide is also plumbous sulfide. You know, lead is a 2,4. I recognize silver. Silver is fixed charged. And so that's silver. And then OH is OH minus. This is hydroxide. Hydroxide is another ide. That's not monatomic. And so this is silver hydroxide. The cobalt's variable charge. So we got to figure out what the charge on cobalt is. But bromide's fixed. So bromide is -1, -1, -1 is -3. So cobalt's got to be 3 plus. And so this is cobalt, Roman numeral 3, bromide. Now cobalt is a 2,3, so this is higher. So this is cobaltic bromide if you want to use the old system. Magnesium's fixed charge. And so this is magnesium ion with hydroxide ion. So this is just magnesium hydroxide. CO3, you got to recognize that. That's CO3 2 minus. CO3 2 minus is carbonate. So this is sodium carbonate. This is silver. Silver's fixed charge of +1, and then it's NO2. NO2 is nitrite. NO3 is nitrate. So this is silver nitrite. Cobalt is variable charge, and so we got to figure out what the charge on. Cobalt's a 2,3, but we have 3 cobalts like this, and we have 2 phosphates. Phosphate is fixed charge. I mean, we know the charge on phosphate is 3 minus. So altogether we have -6. So that means we need +6 for it to come out neutral. So if it's +6 and we have 3 of them, +6 divided by 3, each one has to be 2. And so this is cobalt 2. The other way people do this is they just bring this up. That's a charge on cobalt. Bring this up. That's a charge on phosphate. So you could do that too. But this is cobalt, Roman numeral 2, phosphate. In each box, when given the name, write the formula. And, all right. All right, let's take a look at the first. I guess this is 2 columns worth. So let's look at the first column. Se is selenium. I don't know why they're telling us that. We could just look that on the periodic table. This is selenate. Selenate. This is hydrogen carbonate or bicarbonate. This is neon, which is gas. This is dinitrogen pentoxide. This is nitrite, therefore it's going to make nitrous acid. This is carbon tetraiodide. This is barium. Barium is 2 plus. That means hydrogen can't be plus. This is barium hydride. Hydrogen's got to be negatively charged in this case. Here, it's hydride. This is going to be calcium tellurite. Tellurate is TeO4 on 2 minus. Tellurite would be TeO3 2 minus. This is hypobromite. If that's hypobromite, because bromate is BrO3, bromite is BrO2, hypobromite is BrO. So this is hypobromous acid, you know, hypobromous acid. This is nitrate, and iron's got to be 2 plus because each nitrate's -1. And so this is iron 2 nitrate or ferrous nitrate. Ferrous would be the lower charge here. This is magnesium sulfate heptahydrate. There's 7 waters. We can't see. I don't know. Here, now we can see it. Magnesium sulfate heptahydrate. What is that? Hexahydrate. Hexahydrate, that's weird. Oh, here it is. No wonder. Gallium sulfate. Now, gallium, what group is gallium in? So we look at the periodic table and look at gallium, which is here. Oh, okay, I screwed that up. We see gallium is here. So it's below aluminum. So you'd expect gallium to be +3 like aluminum. And so we'd say gallium +3 here. That's what we do. And so we're going to say gallium is a 3, and then sulfate is 2, because we know from the periodic table, that memorization that we did, gallium 3+, sulfate is 2-. So how many of each do we need? Well, there's 2 ways we can do it. We can cross multiply. A lot of people do that. They cross multiply like this, and that results in 2 galliums and 3 sulfates. Or we can just try to add it up. Or we do this. Right now we have gallium 3+ and we have sulfate 2-. We don't have enough negative charge, so we increase the negative charge. Now we have 4-. We don't have enough positive charge, so we increase the positive charge. That's going to be 6+. Now we have too much positive charge. Then we increase the negative charge, and then it balances 6+ and 6- total. And so it's 2 galliums and 3 sulfates. Perchloric acid. Ic acid is 8, and so we're dealing with perchlorate. Well, chlorate is ClO3, therefore perchlorate is ClO4. So this is ClO4-. And then acid, we just add enough H+. So this is HClO4. Not explosive because H+ is already lost. I already did this one earlier. Lithium, cobalt. Lithium is just Li. It's a metal solid. It's a reactive metal like sodium. Cobalt 2 chloride, hexahydrate. Okay, so cobalt 2 chloride is minus, and so COCl2, and then hexahydrate, we put a dot, and hexa is 6, and then H2Os, and this is a solid. Barium dihydrogen phosphate. Barium is 2+. Dihydrogen phosphate is H2PO4. Now H2PO4 is going to have a minus charge, because of the 2 H pluses. So we'll need 2 of those altogether to balance out the charge. And so we'll need parentheses here. Barium, parentheses, H2PO4, 2. Hydrosulfuric, hydro, ic, means it's got to be sulfide. And so this is repetitive. I've already did H2S, and I talked about it. Magnesium nitride. Magnesium is 6 charge. Nitride is monatomic. Nitrogen likes 3 electrons, so that's it. And so we could do the cross, or we could add it up. And so in this case, we'll need 3 magnesiums and 2 nitrides, or we could just figure it out this way by balancing out the charge. Selenic acid. Ic acid, there's no hydro here. Ic acid just means we're dealing with selenate. And so you got to be quick with the periodic table and be able to see what selenate is. Selenate is SeO4 2-. And so selenic acid, it's got to be H2SeO4, which we already did. Calcium sulfite. Calcium is 2+. Sulfite. Sulfate is SO4. Sulfite is SO3. Charge is the same. SO3 2-. And so here, actually, we only need 1. It's 1-to-1. So CaSO3 is calcium sulfite. This is actually a solid typically too. Sodium hydride. Sodium's plus. Hydride is it's monatomic, H-. And so sodium hydride is NaH, where sodium loses, hydrogen gains. Mercury 1 chloride. Now, mercury 1 is tricky. Mercury 1 is Hg2 2+. You have to memorize that. That's mercury 1, Hg2 2+. Chloride is Cl-, so we'll need 2 of those. So this is going to be weird. It's going to be Hg2 Cl2, 2. Usually we try to keep it the simplest, like a 1-to-1 ratio, but in this case we can't keep it 1-to-1. It's a 2-to-2 ratio. Oops, that was the last one, so let's move on. Okay, so This continues on. Let me see if there's some others that are of interest here. Again, the mercury one is Hg2 plus. Some of these are repetitive. We already did some of these. We haven't done SiO2 though, so let's do that one. SiO2 is, silicon's a semi-metal or metalloid. So we could use two rules for that. We could name it as a non-metal, like a molecular compound. This would be silicon dioxide. Or we can name it as an ionic compound, a metal and a non-metal. In that case, oxide is -2. We have two of those, so it's going to be silicon plus 4. So if it's silicon plus 4, we say silicon Roman numeral 4 oxide. So this is two names, silicon dioxide or silicon 4 oxide. Sulfur is interesting because there's things called allotropes like phosphorus. This particular one is called S8. Yellow sulfur is S8 or just S, you know, if you don't want to do it. Yellow sulfur consists of molecules of 8 sulfur atoms all linked together to form a ring. 3, 4, 5, 6, 7, 8. A ring of sulfur atoms. That's yellow sulfur. S8 or S, solid. S8 more specifically. Just likes to form rings. Let's just focus on, I don't want to repeat a bunch of them. Tin 2 is SN. So tin 2 fluoride is SNF2. This is iron 2 carbonate. Hypochlorous acid is hypochlorite. Hypochlorite is ClO minus. So hypochlorous acid is HClO. Chromium 2 bromide is CrBr2. This one is cobalt 3. You know, I'm bringing this up here. It's cobalt 3. So this is cobalt 3, Roman numeral oxide. I need. This one's sodium sulfite. Mercury 2. Now, mercury 2 is different than mercury 1. Mercury 2 is just Hg2 plus. Mercury 1 is Hg2 plus, but we have 2 of them. And so it's Hg22. Iodide is -1. And so mercury 2 iodide is just HgI2. Aluminum hydroxide is just AlOH3. Here we need the parentheses. It's a solid. This one's ammonium, and then IO3 is iodate. Ammonium iodate. This is selenate, so this is selenic acid. We saw that earlier. This is bicarbonate, so this is nickel 2 bicarbonate because bicarbonate's -1, or hydrogen carbonate. This is copper 2 sulfide, you know, because sulfide likes to get its charge. Therefore, this is copper 2, not copper 1. So cupric sulfide or copper 2 sulfide. What time is it now? It's time for our break. Okay. It's break time. So let's stop here. We're going to take our break now. Let me pause the recording. Oh, where did I put that now? There it is. Okay, so here, this would be the cobalt 3 or cobaltic oxide, sodium sulfite. I think we did those already. Let's see if I have some others that are interesting here. Magnesium nitrite. Copper sometimes. And is this copper 1 or copper 2? We can tell, again here, this is going to be copper 2. Bring that up, or we can just multiply it out. You know, each phosphate's -3, so it's a total charge of -6. We have a total positive charge of +6, so each one has to be copper 2. So this is copper Roman numeral 2 phosphate. Notice when they do the Roman numeral, there's no space here. It's all one word, cobalt, parentheses, Roman numeral 3, close parentheses, all one word. One of the mistakes that students make is they put a space in between here. which seems to make sense, but it's incorrect actually. This is magnesium monohydrogen phosphate. Potassium perchlorate is KClO4. Bromous acid is bromite. Bromite is, well, bromate's BrO3, so bromite's BrO2. So this is HBrO2. This is nickel 2 carbonate. Rubidium sulfate. This is diphosphorus pentoxide. Zinc phosphide. Zinc is 2+ phosphide. This is monatomic phosphorus. So this is a P3-. And so we'll need 3 zincs and 2 phosphides for that. In other words, we could use the little trick here. It's a little shortcut here. If I have zinc with a 2+ charge and a phosphorus with a 3- charge, then I'll just do this. I'll bring the 2 down here and the 3 down here. And so it's going to be 3 zincs and 2 phosphides. That'd be there. Sodium hypochlorite. And so I always do this. I do it quickly because I know ClO3 is chlorate. So chlorite is 2. Hypochlorite would be 1. And so sodium hypochlorite, ClO-. Oops, ClO-. Sodium is plus. So sodium hypochlorite's bleach. This is bleach. Bleach is a chlorinating agent. So bleach has some chlorine. Chlorine wants electrons. Bleaching is oxidizers. You want oxidizers to do bleaching. And so when we look at this, oxygen has its normal charge of -2. That means chlorine's +1. Well, chlorine at +1 is still not happy. Chlorine likes to be happy at -1. And so this is a good bleaching agent because of the chlorine in here. Wants electrons. Oxygen doesn't need any electrons. It's good. Even though oxygen is considered a good oxidizer, chlorine's better here in this case because oxygen's already taken its electrons. And so that leaves chlorine. Now this is rubidium sulfate. Actually, where am I? Cesium nitrate. I guess I got mixed up here. Cesium nitrate is cesium is plus, nitrate is NO3-. And so CsNO3 is cesium nitrate. Let's move on here. Okay, that was, this is the last one actually, 86 here. N2O3 is dinitrogen trioxide. Dinitrogen trioxide, that's an interesting charge because nitrogen's in the +3. You can see it if you reverse the cross multiplication I did. Oxygen's -2, nitrogen is +3. I'm doing that. And this is dinitrogen trioxide. Manganese is a 2,3. This is manganese 3 because we have 3 hydroxides. Each hydroxide is -1. So manganese has got to be +3. Magnesium is always 2+, sulfate's SO4 2-, so MgSO4. Then mercury 2. Mercury 2 is Hg2+. Mercury 1 is Hg2 2+. So mercury 2, Hg2+. Bromide is bromate is BrO3. Bromide is BrO2. So Hg2. This would be it. Hg2 plus with 2 bromides should do it. 1, 2 bromides. So this is going to be Hg parentheses BrO2, 2. That's a mercury 2 bromide. All right, that was the last one. I only did the even ones, or I guess the odd ones have the answers. So I did all the evens, or not all because I skipped some. Some were kind of repetitive, so you can skip those. Let's go on here to what I need to cover for today. What I need to cover for today is chapter, oh, I guess I don't have it. Chapter 2, I don't need that. Chapter 6, I need that. This is chapter 6. On chapter 7. So chapter 7, you know, chemical formulas tell us the composition. They tell us the atom composition, you know, and so how many atoms of each element do we have? And so let's go call it atomic composition. And so And look, water, you know, look at the composition. Water is H2O, 2 hydrogens for every oxygen atom. This is a drop of water, okay, hitting the surface here. So 1 drop must hit the surface. And if we could visualize the particles of water, we'd see the water molecules. And the water molecules are being held together. You know, this drop doesn't just easily break apart. The drop stays together. And they're being held together by these dotted things. These dotted things are what we call hydrogen bonds. Hydrogen bonds are electrical attractions. This little symbol here is delta. It's a delta minus. The oxygen has what we call a partial negative charge. Delta means partial. So partial, and the hydrogen is a partial positive charge. Not a full positive charge and a full negative. A full positive and full negative charge would be like the ions, you know. This is partial, and that's what holds the water molecules together, these hydrogen bonding interactions. I don't know what this one means. I got this from Wikipedia. I forgot to reference that. This is just taken from Wikipedia. And this is taken from Pexels. This is a nice picture. And so I tried to show that here. But how many water molecules are in the drop of water? Well, in this chapter, we can calculate that. We can figure out how many water molecules are in that drop of water. You know, the water molecules are tiny, you can't see them. And if you try to count them, it would be impossible to count. Even if you took all the people on Earth and had them count, you know, in parallel, that is, you know, you divide up all the water molecules and have people count them, it would be impossible to count within everybody's lifetime. There are just so many water molecules. I mean, they're just so tiny, you can't see them. And so, well, stepping back from that, let's first take a look at the chemical formula. Chemical formula is the atom composition or the mole composition. Mole composition is just a mole's like a counting unit, you know, like a dozen. And so, for example, if I have 2 hydrogen atoms, I have 1 oxygen atom. If I have 2 dozen hydrogen atoms, then I'd have 1 dozen oxygen atoms. If I have 2 moles of hydrogen atoms, I'd have 1 mole of oxygen. So it's a counting unit, like a dozen. That's what we have. And so it's the atom or mole composition. So let's take a look at some of these, you know, like perchloric acid, we saw, or perchloric acid is HClO4. Perchloric acid is a strong acid, and it consists of 1 hydrogen, 1 chlorine, and 4 oxygens in there. And so as far as composition goes, we have 1 H atom per 1 HClO4 molecule. And so I know there's 1 hydrogen atom in every perchloric, etc. You know, for example, there would be 4 oxygen atoms in every 1 HClO4 molecule, you know, etc. We could do lots. Or we could do something like this. We could say that there are 4 oxygen atoms for every 1 chlorine atom. But this is restricted, you know, all these are only for perchloric acid. This is perchlorate. Perchlorate makes perchloric acid. And so we can get these ratios, you know, we can get these composition ratios here, and we could use these composition ratios as conversion factors. We can carry these composition ratios to this. Like, for example, I could say that rather than 1 H atom, I could say 1 dozen H atoms. Okay, if I have a dozen H atoms, then how many molecules must I have? Well, I must have 1 dozen molecules of perchloric acid, HClO4. You know, because each molecule gives that. And so we can have that. Or, you know, a mole. We could have 1 mole, which is like a dozen, except it's much huger. Dozen's 12. You know, if I have a dozen, I have 12. So this is 12 H atoms for every 12 perchloric acid molecules. A mole is 6.022 times 10 to the 23rd. It's a huge number. But if I have 1 mole of H atoms, then I must have 1 mole of molecules here. Molecules. And so whenever I see a dozen, I replace it with 12. Whenever I see a mole, I think 6.022 times 10 to the 23rd, which is a huge number compared to a dozen. You know, 12 molecules, you can't even see that. But with 6.022 times 10 to the 23rd, you can see that, you know. For example, if I had 6.022 times 10 to the 23rd water molecules, that would be equivalent to 18 milliliters of water. So it's a significant amount. It's a macroscopic quantity of water molecules. And it's easy to see. So this is why we want a huge number here, so we can bring that into macroscopic quantities. So this is the atom or mole composition we're dealing with here. This. Now, one thing is, how much does it weigh? And so, how much does it weigh? Well, a question that's somebody brought up, Kyle brought up earlier, is we're missing one isotope of hydrogen. You know, if you know hydrogen isotopes, we have names for these. For example, the first one is called hydrogen. You know what the second one is called? It's only for hydrogen that we have these names for. But has anybody heard the name for the second isotope of hydrogen? It's given a special name, and it's unusual to be given a special name because most of these aren't given any special name. And so this is hydrogen 1. But this one has a common name. It's called deuterium. Deuterium is hydrogen 2. This is a little heavier version of hydrogen. But there's one isotope missing in here. The one isotope that's missing is H3 with a 1. And yeah, that's tritium. One of the reasons why tritium is missing is because it's unstable. This is radioactive. Its nucleus has too many neutrons. It's radioactive. Tritium. However, tritium does occur in nature, but just to trace quantities, you know, the percentage natural abundance of tritium is very low. So if you have a glass of water, chances are you drank no tritium. Tritium is not healthy. It's not good for you because it decomposes. But let's radioactively. Let's take a look at where we can find that. Well, actually, we could find that information in the Chem 1A book. This is the table of natural isotopes from the Chem 4 book. But let's take a look and see if the Chem 1A book has it. And so I'm going to go back to the Chem 1A book. Here. And then clear all the drawings and then take a look. It's in Appendix D. The D stands for data tables. This is something we'll talk about later. These are electron configurations here. It's not it either. Yeah, I guess I'm going to have to scroll through all these. Probably should just search it. It's A27. They should have put it at the beginning. Let's go to A32. Yeah, overshot it probably. Let's go to A30. Yeah, here we are. So if we go to the Chem 1A, this is in the Chem 1A book, Appendix D table here. We look at hydrogen, and then deuterium is the second one. And then we have the natural abundances here. You know, if you look at the natural abundance of tritium, it's blanked out there. It's negligible. The same thing, one isotope of carbon is missing, carbon 14. Carbon-14 occurs naturally due to cosmic irradiation. Its natural abundance is negligible here. It's negligible. So even though trace amounts do occur, we're going to ignore it. In fact, let's take a look at what that abundance is, since they both ignore it. Tritium, natural abundance. It occurs in natural water with abundance of 10 to the minus 18. 10 to the minus 18. Natural abundance. Now, what is that? 10 to the minus 18%? There are no units there, so I hate that. When there's no units, I don't know what the heck they're talking about. 10 to the minus 18 means 1 part in 10 to the 18. That's a problem. That's it's not clear when they don't have the units there. It occurs in natural water with an abundance of 10 to the minus 18 of natural hydrogen. So it's 10 to the minus 18. I think that's parts. But you have to be careful because there's atom ratios and mass ratios. So they need to be more specific as to what they're talking about. And so anyway, if it has this low of abundance, then, most of the time, you're not going to see it. Any tritium, is discovered, here. And so what we're going to do is the natural abundance of this is so low, we're going to say it's negligible. Probably we shouldn't, but we're going to just say it's negligible because in most water samples, you're not going to have any tritium. Okay? And so that's what the book is doing here in this particular instance. It's so low. Same thing with carbon-14, so low, it's not going to be so significant. So that's what we're going to do. Now, how much does a molecule weigh? And so let's figure that out here. So what time did we start again? Yeah. So how much does a molecule weigh, or a formula unit weigh? It depends on what atoms it's made of. Some are going to weigh more, some are going to weigh less. It depends on, let's look at H2 as an example. If we look at H2, it depends on which isotope of hydrogen we're doing, because one isotope weighs about twice as much as the other. H1 weighs about 1, H2 weighs about 2. It's twice as much. Tritium weighs 3 times. It's 3 times heavier. Oops, it's not missing. It's missing here, but it would weigh 3 times as much. And so what we have to do is we have to specify which isotope. And so if we're dealing with H1 bonded to an H1, this will be H2. And so we have a hydrogen 1 bonded to a hydrogen 1. Then it's going to weigh this. It's 1.00. This one weighs 1.00782. 50321. 50321 U. This one weighs the same amount. It's the same. And so this one's going to weigh 2 times that. Well, what is 2 times that? So 2 times that would be 2 times 1.00782. 50321. 50321. And that's going to weigh. And so this whole thing is going to have a molecular mass is going to be 2.0156500 64 U. That's its molecular mass. That's a lot of digits. All right, but we have other molecules. For example, we could have an H1 bonded to an H2. And this is going to weigh a different amount. It's going to be this plus this. And so how much does that weigh? It's going to be 1.00782, 50321, plus, how much does an H2 weigh? An H2 weighs 2.01, 2.01, 41, 01, 7780. And so this one's going to weigh 3.02192,681. And then we could have an H2 that's bonded to an H2. And so there's two H2s. If it's two H2s, it's going to be double. So 2 times 2.01, 41, 01, 7780. So, and oh shoot, what did I just do? Yeah, I screwed up. I didn't clear something in my calculator. Anyway, it comes out to 4.02820, you know, et cetera, U. This is U. So some of the hydrogen molecules are lighter, some are heavier, you know. But in a sample of hydrogen gas, how many molecules of hydrogen gas do we have in a sample? We have a huge number. And so if we're looking at a macroscopic, let's say we're looking at 1 liter of hydrogen gas under normal conditions. Actually, 1 liter of H2 gas. We have basically an uncountable number of hydrogen gas molecules in there. There's just going to be a huge number of H2 molecules. Most of these will be H1, because the percentage abundance, 99.99. In fact, practically all of them are going to be this. It's going to be greater than 99.9% of this. But a small fraction of these will be heavier ones like this. But we don't want to separate it. So, you know, if we're taking a huge number of these, okay, if we work with individual molecules, then we need to know how much does that individual molecule weigh. If we're dealing with individual molecules, then are we doing an H1 and an H1, or an H1 and H2, or H2 and H2? We need to know. But if we got just a huge number of molecules, then, okay, this is like this. Let's say you're at a huge event, you know, 1,000 people are at this event. And then you want to say, okay, you know, you measure each person's height. So we look at everybody's height, you know. And just as an example of a quantity, do you want to measure every single person's height, you know? Or do you just want to take the average? You know, the average person's height is about this, you know, and then you can see the average. Well, once you start getting into huge numbers, you don't want to deal with individuals. You want to deal with the averages. Otherwise, it just becomes too horrendous, you know, to have to do individually every person's height and weight or whatever you do, you know. And so in this case, we want to just take the average mass of an H2 molecule. And to take the average mass of an H2 molecule, we need the average weight of an H atom. Well, what is the average weight of the H atom? The average weight of the H atom is given in the periodic table. This is the average weight or average mass of an H atom. Now, it's an average, but it's not a straight average. This is a weighted average. And so all we do is we weight it by percentage. And so 99.9885% are this. And so where this number comes from is we take the percentage, 99.9885 out of 100, you know, percents part per 100, are going to weigh 1.007825031U. Plus, okay, then this one is the other part, is going to be 0.0115 out of 100 will weigh 2.01411, oh, excuse me, 017780 U. And so doing this, so we're going to get the weighted average. So let's go ahead and calculate this right now. 99.9885 divided by 100 times 1.0078250.321 equals, plus parentheses 0.0115 divided by 100 times 2.014101778, close parentheses, equals. And so I get the average, weighted average is 1.07940,754U. So this is the weighted average. Well, to 5 sig figs, what is the weighted average? To 5 sig figs, the weighted average is 1.0079U. That's the weighted average of the hydrogen. So we figure out what the average hydrogen weighs. And so we come up with the average hydrogen molecule. The average hydrogen molecule is going to be a mix of these 3 molecules. These are the 3 molecules that make up a sample of hydrogen like this in nature. And so the average hydrogen molecule is going to be closer to 1 than it is to 3 and 4. I mean, it's going to be closer to 2, sorry, than it is to 3 and 4 because it's 99.9% or more. Actually, to figure out the percentages, we take a fraction of a percentage. I can show that, but that's what we do in Chem 1A. I'm not going to do that in Chem 4 here. I can figure out the percentage natural abundance of these molecules by taking a percentage times a percentage, but a percentage times a percentage gives us percentage squared. So I got to convert one of these percentages in decimal form and then multiply by percentage. Ignore that if you want, but it's part of statistics. And so this is a hydrogen. The average hydrogen is going to be double the average weight of a hydrogen atom. The average weight of the hydrogen atom to 5 sig figs is 1.0079U. So the average hydrogen atom weighs, what is that? 2 times 1.0079. We'll just do it to 5 sig figs here. Oops, it's going to be 2.0158U, like that. That's what we're going to have. So that's the average. Hydrogen molecule is going to weigh that. Okay. Let's do the same thing for H2O. So what is the average oxygen weighs? The average oxygen weighs about 15.999. But when you look at oxygen, you know, we have 3 different isotopes of oxygen. One is oxygen 16, which weighs 15.994. Okay. Then we have oxygen 17, which weighs 16.999. And then we have oxygen 18, which weighs 17.999. And we look at the percentages, it's mostly oxygen 16, so the average is going to be very close to 15.994. It's a little bit higher, it's 15.999 because we got a little bit of the heavier ones here. Just a small fraction of the heavier ones there. And so that's why it's a little bit higher there. Okay. So what about water? Well, if we're looking at individual molecules of water, then we have to know what we're dealing with. And so in this case, if I have an H1 and an oxygen 16 and an H1, this will be the lightest. And then we have different variations. You know, when you have a glass of water, how many different water molecules are you drinking? Mostly this one, because most of the hydrogen is H1 and most of the oxygen is O16. So when you have a glass of water, it's pretty much all this one. But there's going to be a little bit of this, H1, O16, H2, and there's going to be some of this, H2, O16, H2. That's O16. Then we have O17. And so we might drink H1, O17, H1. There's a little bit of O17, not much. And then we might also have H1, O17, H2. or we could have H2O17 H2. And then there's one more, there's O18. So we could have H1 O18 H1, or we could have H1 O18 H2, or we'd have H2 O18 H2. Okay, the lightest one is going to be this one. Okay, that's the lightest one, and we can figure out what the mass is. Just add 2 times this plus an O16, which is this. It's going to come out around 18 U. The heaviest one is this one, and so we have 2 deuteriums, so we take 2 times that, which is about 4, plus an O18. O18 weighs about 18, so this one comes out to about 22 U. This one comes to about to 18 U. So this is the heaviest water molecule. Actually, the heaviest would be with tritium, but there's barely any tritium. And so we'll ignore the tritium. The heaviest would be with tritium, O18, tritium. But for right now, the heaviest is going to be deuterium, O18, deuterium at about 22 U. Tritium would be 3 plus 3 is 6 plus 18 is 24 U. Tritium would be even heavier by about 2 U. So we could figure out the specific masses of each of these molecules to a lot of sig figs, you know, just by adding that up. But when you had the glass of water, how many water molecules were there? They're innumerable. I mean, you can't even count how many there are. You know, we could calculate how many there are, but you can't count them one at a time. If you would count them one at a time, you would lead a futile life because you'd never reach your goal and you waste your whole life counting water molecules. Even in that single drop, you couldn't count those in a lifetime. And so what we do is if we have a large number of water molecules, then we don't care about the individual water molecules. The individual water molecules are gonna, let's see how much the heaviest one weighs. I'm just curious how much the heaviest one weighs. It's gonna be 2 times 2.01, 41017780 equals plus the oxygen 18. Oxygen 18 is 17.9991604. So the heaviest one of these is 22.02798.076 U. That's a lot of sig figs. That's how much the heaviest one weighs. Well, what does the average one weigh? So just like we did for hydrogen, we can get the average atomic mass of oxygen, except we need 3 terms because there are 3 isotopes. We need 3 terms. So let me just set that up really quick to show you how we do that. Since there was a question about this the other day. And so calculating the average atomic mass of oxygen, first isotope is oxygen 16. And so 99.757 out of 100 are oxygen 16. And each oxygen 16 weighs 15.994914622 U. It's the first term. The next isotope is oxygen 17 at 0.038 out of 100. And that's going to weigh 16.999135150 U. And then the last isotope is oxygen 18 at 0.205. So this is 0.205 out of 100 are going to weigh 17.9991604. And so what does the average oxygen weigh? Let's get it to a lot of sig figs here. The average oxygen is going to weigh 99.757 divided by 100 times 15.994914622 equals, plus the second term, parentheses, 0.038 divided by 100 times oxygen 17 is 16.9991315, close parentheses, equals, plus parentheses, Oxygen 18 is at 0.205 out of 100 times oxygen 18 weighs 17.9991604, close parentheses, equals. And so the average oxygen weighs 15.9940493. And to 5 sig figs, it's 15.999. Oops, 99. Sorry, I miswrote that. This is equal to 15.99949940493 U. And so to 5 sig figs, 15.999. And so what does the average water molecule weigh? The average water molecule weighs, well, what does the average hydrogen weigh? The average hydrogen weighs this much, so 2 times that, plus the average oxygen. Now we're going to be doing averages. And we don't have to be so precise. When we do the averages, our goal is 4 sig figs. 4 sig figs. Therefore, use 2 decimal places. Except for hydrogen. Hydrogen is 3 or 2, except H. H is 3 or 2 decimal places. This is to make the calculations rapid. You know, there's too many digits here. And so if I want H2O rapid, this is what I'm going to do. I'm only going to use 2 decimal places. That way, it becomes a little easier to memorize certain things. And so let me tell you what I mean here. If I do hydrogen, I use this. I use 1.01 or 1.008. So I'll round that to 1.008. For carbon, I use 12.01 U for the average. These are all U. For nitrogen, I use 14.01 U. For oxygen, I'm going to round it to 2 decimal places. So it's going to come out to 16.00 U. These are common ones, very common ones. And so let's see. Just 1 second, I need it. All right, so here, hydrogen, I need to use the one that's going to give me 4 sig figs at the end. In this case, when hydrogen is in the element, use that. When hydrogen is in a compound, use this. So water, hydrogen is in a compound, so we're going to use that. And so H2O is going to be this, 2 hydrogens at 2 times 101, which gives me 202 U. And then I have 1 oxygen, 1 at 16.00. This gives me 16.00 U. And we add these up, it gives me 18.02 U, which is 4 sig figs. And so the average water molecule weighs 18.02 U. That's what the average water molecule weighs. Okay, we aren't going to go 3 decimal places. We aren't going to go 4 decimal places. We're either going to go, we're going to go for 2 decimal places for most of them, or 3 when hydrogen's alone, like in H2. H2, we wouldn't do 202. If we do 202, that's only 3 sig figs. That's not enough. 3 sig figs is not enough. And so we're going to have to use this one, 1008 times 2. That's going to give me 2.016 U. That's 4 sig figs. And so that's when we'd use that. Is that clear? it's still recording, yeah. I'm going to clear the drawings here. Now, when we're dealing with a lot, you know, a dozen, you know, the dozen's not enough. You know? We need a much bigger counting unit, and the much bigger counting unit is the mole. And so let's talk about the mole, what the mole is, the definition of the mole. One mole is defined as the number of, well, number of units. In this case, the units are going to be atoms in exactly 12 grams of carbon-12. And so what we do is we figure, okay, we could say this, exactly 12 grams of carbon-12 contains approximately 6.022 times 10 to the 23rd carbon-12 atoms. This number here is called N sub A, which is Avogadro's number. Avogadro's number is what we use to call a mole. So 1 mole of anything is 6.022 times 10 to the 23rd of those anythings. And so this is a mole of those. Equals a mole. So why did they pick this number? Because carbon-12 is unique. You know, why this number? Okay. Because the AMU, what was the AMU defined as? AMU is the atomic mass unit again. Recall that the AMU is defined like this. There are exactly 12 AMU in a single carbon-12 atom, like that. Like that. And so what happens is the duplicate relationship. There's exactly 12 grams in 1 mole of carbon-12 atoms, or 6.022 approximately times 10 to the 23rd carbon-12 atoms. So there's a parallel relationship. And the relationship is between numerical, it's a relationship, a numerical relationship between atomic, molecular, formula unit, mass and something we call molar mass and molar mass. So a single carbon-12 atom weighs 12 AMU. A mole of carbon atoms weighs 12 grams. And so this is U per unit. AMU per unit. So U per unit. This is grams per mole of units. And the number is the same. The number is the same. Let's look at an example here. I'll do an example here instead. Okay, oops. I thought I had a different slide next. How much does the average water molecule weigh? The average water molecule weighs, we just calculated at 18.02 U. That's the average. And so if I have one average water molecule, it weighs 18.02 U. Actually, none of the water molecules weigh 18.02 U. That's just the average. However, if I have 1 mole of H2O molecules, how much would it weigh? Well, 1 mole of H2O molecules is going to weigh 18.02 grams. How many water molecules is that? That's 6.022 times 10 to the 23rd H2O molecules. Water's density is about 1. So this is about 18 milliliters. So 18 milliliters is a mole of water. 18.02 milliliters is a mole of water. And a mole of water contains 6.022 times 10 to the 23rd water molecules. How many is that? So 602, we'll move it to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So can you count that? Let me make sure I did it right. I better double check my count here because I could have screwed it up. Let me erase this down here. So I'm double checking my count here. Let's make sure I got it right. 6, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yep. And so that's going to be 1,000, million, billion, trillion. I can't go beyond a trillion. 1,000, million, billion. Is that right? Let me see if I got this right. So this would be 602 billion trillion water molecules. So if I had 18 milliliters of water, which is about 18 grams, which is a mole of water, I would have 602 billion trillion water molecules. Can you count that? Starting with 1? No, you're not going to be able to count that starting at 1. But we could calculate it. Well, we didn't have to really calculate it. It's just based on how the mole's defined here. So just an interesting way of defining it. And so we get the numerical relationship here. Okay, let's move on here. This is a mole of different things. So the average, you know, the average nitrogen molecule, how much does the average nitrogen molecule weigh? The average nitrogen molecule weighs this. I'm going to just do it. You know, nitrogen, the average nitrogen is 1401. So if I have 2 of those, it's 2 times 1401. So the average nitrogen molecule weighs 28.02 U. If I had a mole of nitrogen molecules, it would weigh 28.202 grams. And so this is the way I use these. I could use these in 2 ways. One, I could do this. I could say 1 N2 molecule. There's 28.02 U of N2. So 28.02 U's per N2 molecule. Or I could go 28.02 grams of N2 per mole of N2 molecules. So in this balloon, there would be an Avogadro's numbers worth of nitrogen molecules inside this balloon. Too many to count. This balloon's too small, by the way, under normal conditions. Here's a mole of iron. The average iron atom weighs 55.85 U. A mole of iron atoms weighs 55.85 grams. How do I know the average mass of an iron atom? I can look up the average mass of an iron atom on the periodic table. The periodic table tells me what the average mass is. So let's go back to the periodic table and see, do I have that here? Hopefully this will give it to me. $55.845. So we're going 2 decimal places. So rather than saying 55.845, we're just going to call it 55.85. And so the average iron weighs average iron atom weighs 55.85 U. A mole of average iron atoms is 55.85 grams. And so there are 2 units for these. You see, these have no units. The 2 units are U per atom or grams per mole of atoms. And so there are 2 units for all these. Let me just write that down here. The 2 units we have is 55.85 U per iron atom, single iron atom average, or 55.85 grams per mole of iron atoms. And so the 2 units are U per unit or grams per mole of units. That would be the 2 dimensions we do. Moles are considered macroscopic. You know, we could visualize. You could visualize 55.85 grams. You could see that, but you can't see 55.85 U. That's particulate level. We need, you know, an scanning electron microscope to see that. And so let's go back to our PowerPoint slide here. Delete these drawings here. Why did it go out of slideshow mode? So these are all macroscopic. Here's a mole of iron. That's what a mole of iron looks like. Here's a mole of aluminum, which is 27 grams worth, or 26.98. Here's a mole of mercury, which is 200.6 grams. We get these all from the periodic table. These numbers just come from the periodic table. Sodium, 22.99 grams per mole. Copper, 63.55 grams per mole. Oh, we can see this. This is, what's the name of this? This is copper 2 sulfate pentahydrate. You know, the water molecules are stuck inside the crystals. It's 249.69. We take the average copper, add it to the average sulfur, and then we got 4 oxygens. And so this, and then we got the 5 water. So let's calculate the molar mass of this or the formula mass of this as an example. So we'll do that as an example here. This one is a little bit more complex. And so what does copper 2 sulfate pentahydrate consist of? It consists of 1 copper. And so what's the average mass of a copper? So we have to go to the periodic table and look at the average mass. Now we're going to do it grams per mole or U per atom. We're going to do it grams per mole because we deal mostly in the macroscopic right now. And so that's what we're going to do here. And so let's go back to the periodic table and look at copper. We need copper, and I know sulfur already, but copper Let's find out what its average is. Okay, we only want it to 2 decimal places. So I'm going to call copper 63.55 U. 6355, remember that number. And sulfur, we're only going to use 2. So sulfur, I'm going to round it, 32.07. I know I told you there's only one rounding step, but for these masses, we're going to round them. So because the periodic tables do that already. So your periodic table only shows 2 decimal places, so yours are already rounded. 3207 and copper 6355, okay? 3207, 6355. So copper is 63.55 grams per mole. We're going to go macroscopic now, 55. Sulfur, 3207 grams per mole. Then how many oxygens? We have 4 oxygens here plus 5 oxygens there. We got to account for the water stuck in there because the waters weigh something too. So altogether there's 9 oxygens. So that's 9 times 16.00 U. Oxygen 16. 9 times 16, what is that? 9 times 16, 144. So it's going to come out to 144. And I'm going to go 2 decimal places. I'm not actually allowed that one, but I'm going to do it. 9 oxygens and then 10 hydrogens from the waters. Hydrogen, we could use 101 for that. 9, this didn't come out right. That's pretty hard to see. Nine total oxygens, so 9 times 16. Then 10 total hydrogens. Oxygen, this is hydrogen, this is sulfur, copper. That's 10 times 101. 10 times 101 is just 10.1. And so let's add them up. Add them up, 63.55 plus 32.07 plus 144 plus 10.1. And I'm going to go 2 decimal places. And so it's going to give me 249. 249.72 U. We're off a little bit because it depends if they rounded it or if they didn't. We're within round off error, 24.69 versus 249.72. And so water, we already did that. It's 1802. Mercury 2 oxide, we could do that one here, HGO. Oxalic acid, this is a different way of writing oxalic acid. The way we would have written oxalic acid is H2, C2O4. C2O4 2 minus is oxalate. Oxalate gets changed to ic acid, so oxalic acid. This is a different way of writing it here. This is oxalic acid dihydrate. So this is anhydrous. Anhydrous means without water. And so you bake it in the oven, dry out the crystals here. These weren't baked out. It forms a stable hydrate. So this is the dihydrate here. We can figure out the mass. You got to count for the hydrate mass. You know, the 2 waters, about 36 grams extra. So it's about 36 grams more than this. I guess it's time for a break. Let's take a break now, and then we'll take a 15-minute break here. And stop the recording.